Peter, can you hear us? Sound is muted. Presente? No, ok, sono le 10. Provo. Ma in teoria il microfono funziona. Can you hear us? Niente? Già. Sì, ok. So, welcome, everyone. Beautiful civil informatics and aeronautical technology department. Very glad that we can host the Miria final event that location. Coffee break. Let it start. I won't bother you for more than 5 minutes. I just want to present our facility and the material science to one that was today. So, Roma 3 has been established in 1992, and these numbers are a little bit outdated, I would say. So they've grown a lot. For that in mind. The material science and technology is part of the department of computer science, aeronautical technology department. They decided to. The group has 5 permanent staff, 1 full professor, 2 associate professors. Then there is 1 senior technician, 1 senior technician, 3 assistant professors. Yes. 2 postdocs, students, and then we have clinical fellows and 10 yes. You can see 2 pictures. As I've said, like there are 2 associate professors project, and these 2 associate professors divided into 2 main branches. We have our branch, the one, which is on surface proteins chemical testing, and biology, synthetic engineering in general. And then we have another group by Professor Miria Langara. They are leading the part of morphing materials and components. So that's the core of the group. That's all. Yeah, starting everything. So very briefly, we have a lot of projects running. Miria is one of them. Among Miria and with Miria, we also have another project, Digital. One national project which is called zirconia ceramics. Then we have Cooperate, the project artificial intelligence. Nanometronics gets finished and was a project on techniques. Mecanano, we had the final event hosted here a couple of weeks ago with a post action. So an action just to have researchers join together and do dissemination activities on testing. And of course, within Miria, the one that we hosted today on the development of antimicrobial. The facility that we have in the group is mainly funded by one national project, which is called Alien Trends. And this project is on the establishment of research facilities, national research facilities, and we gained some funding for our instruments thanks to the national funding. What you would see in our facility, you already know, is the macro, micro, and nanoscale mechanical testing. So we have macro scale harness testers, we have micro scale harness testing, and our core techniques are based on techniques. So you see, we have two excipients testers, 200 and the proteins, and then we have two in situ microbes, which goes into an STM microscope and see what it does. Then, of course, we have all the microscopy facility, a dual beam STM and FIB microscope. TM is being renewed, so we will have a kilovolts installed by September. Atomic force microscopy, and then, of course, the X-ray spectrometer, looking at bulk materials and optical microscopy. I wanted just to briefly present you the group and the facility. You already know the project, and just leave you with on a scale with lab, and you can have simulation samples and scale materials as it is manufactured. So I leave the floor to Angelo, I guess, within the work package one presentation. And thanks a lot, and I'm glad we can ask you.
Hello, everyone. Thank you for being here. Thanks, everyone. Geraldo. So for the other, just one comment. There are two different meetings for today. One of them was sent by me, and the other one was sent by Chiara. Yesterday I sent an email. I know it was late, but if there are some problem, you can just check the email and you can access this present meeting by clicking on it. Okay. So thank you everyone for being here. This is the final meeting of the Miria project. Just for context, what is Miria? Miria is about the development of antimicrobial, antiviral, and fungal monocoatings for everyday surfaces. So as you can understand, the general objective is exactly that, to have at the end of the project some coatings that are effective against a wide range of microbes and viruses and fungi. So some of you might ask, why are we here? Because the context of the Miria project is basically born from the COVID pandemic. And we are here because history repeats itself. And repeats itself because we never learn. Because certain topics, certain events, we did them, and we want to forget them because they're very distressful. In fact, one of the real objective is also to lower the psychological effect that a possible pandemic can have. And so this is also has been treated recently in some articles in the newspapers, such as why we don't talk about COVID anymore. But COVID is still here. It has been changed. It is manageable. And this is due also to some of the European Union concerns that we have dealt with during the project. Currently, for instance, in the UK, there are still some vaccines being delivered and applied to the most the most sensitive people, and so it is not been completely defeated. But beyond that, even if we want to forget about it, uh, as you know, very recently, we are talking about the next pandemic. And, and what is wrong with that is that even though we have gone through such a distressful time, we do not want to think about it. And so instead of thinking about how to unite people and try to fight a common enemy, which we see that we want to fight with each other. Besides that, we need to be united. And so I think the project is also the perfect example for this because it is from 15 different partners coming together for a joint objective and from different nations within the EU. And I would like to thank all of you. I will do that in a moment. But first, I would like to thank the first person who was the coordinator of this project, Dr. Mario Tuli, and I would like to ask him to come here to say a few words. Round of applause for Mario. Don't worry, just few minutes. Just few minutes. I can't imagine how glad I am today. I mean, remember the starting of the world of the media about 5 years ago. Years ago, the first contact with the BPP decided to start this project. The first version, the first meetings, and maybe some other group that was represented. And remember the first version of the project setup. You remember that the vertical lines of the code is crossing the horizontal lines of the applications. I have to say that I was profoundly unsatisfied about that setup of the project because I saw it as a mechanical assembly by separated parts of all the partners developing his own coding
weekly way. But when I was informed that there was a new partner joining the consortium, Albo, and I remember during the first meeting of Albo attended, Dominique showed us their works in their activities in the field of the um, operational theater. And we saw the opportunities to have a unified environment, to unify all the case study, a strong case study to have all the application put together. And I remember with the help of Angelo, we wrote the project from the ground and sent it for approval to the partners 10 days before the deadline. And it worked, not only because we had the project approved, but also because we managed to create a working environment to put together all the partners, all the activities, and having an effective uh, interaction and between the activities of the several partners. And this, let me say, it's a satisfaction from me from the professional side, but also from the personal side, because I participated in several projects in my professional life and as a partner, as a coordinator, but it's not so frequent. These strict relationships between the partner is a very good working and personal environment. So I've been kept informed by the progress of the project of Angelo. So I see that almost all the objective of the project has been fulfilled and that all the acceptance of threshold have been overcome. Well, as I told them, it was a very, how can I say, uh, I'm very proud to have contributed to this project. And I thank you for cooperating. So enough is enough. Angela has been so kind to invite me for the social dinner this evening, and I will be glad to be each of you this evening. So
You can also eat the social dinner. Okay. Mario. So something thrilling to have you back here. Uh, Before moving on, I would like to remind you to sign the participation sheet to for your complete participation in it. We can also have some uh, documents for you about the participation if you need it. Okay, so moving on, I would like to thank and I would like to go more into detail about some of the Miria consortium partners. Some of this presentation I received very recently, so I would have to switch sometimes from the presentation to the slides which are outside this one. So I would like to thank those we have the academic institutions. I would like to go closer because I cannot see, such as Alliance Tian. I know it was already presented, but I would like to thank them, and Charles University. And so for what about Alliance Tian, I don't know, Pierre, if you want to say a few things.
Like Edoardo said already, we are focusing on design as materials from the mechanical and nano and microstructure.
Yeah, I asked her because it's close. She's close. And I would like to thank her because she organized together with today's meeting. So the next one is the Chelsea University. Chelsea University was founded in 1348. It is the oldest and largest university in Czechia. It has 17 faculties and it has a very great expectation and numbers about the Faculty of Sciences. And you can see in the picture the group about photochemistry and supermolecular chemistry of porphyrinoids, which is led by Professor Mossinger, and which has participated in here. Then we have the public research centers such as CNRS, BPT, SEA, and IMN. About CNRS, sorry, I need to go check. I'm not showing anything here. Okay. Okay, I'm sorry. We received it very late, and I wasn't able to merge it into the final presentation. So I would like to thank Thierry Rabiou, Véronique Colinfort, Elizabeth Chartier Garcia, and Elizabeth Daroussa. They have provided toxicity testing for nanofillers developed within Miria. Okay, we'll go back to the presentation. Then we have SEA. I would like to thank, of course, Sylvie Modelier. SEA is the French Commission for Atomic and Alternative Energies. Is a key research player in defense and security, digital sciences, future healthcare, and low carbon energy. The Laboratory for Innovation in New Energy Technologies and Materials, which is called LITEN, primarily focuses on the development of new energy technologies such as renewable energy efficiency, storage, and innovative advanced materials, such as nanomaterials, to support them. In Miria, SEA LITEN is responsible for the design and implementation of experimental tests complementary to mechanical tests to validate the durability of the novel proteins. Next up, we have the reproducibility, which I think profoundly because, as Mario said, was the first contact and the first one we shared a common idea and design of the project. You can see here the group who collaborated with Miria, and I would like to thank each and every one of them. I hope not to miss anything. Dr. Sapusari, Dr. Malin Domberg, Diana Rotary, Dr. Petriditsen, and Dr. Tuomo Hilt. Next up, we have also the group from IMM, and I need to go closer. Can I probably pass it down? Thank you. Sorry. Sorry. Coordinating is making you understand you need to sit down sometimes. So look, I said IMAN is the main research and development center of the portion of ferrous industry, specializing in development and implementation of innovative technologies of metal value recovery and advanced materials applications across the large part of non-ferrous metals value chain. Their role was to develop a synthesis procedure for ultrafine antimicrobial powder materials such as the oxide of copper, the mixed oxide between copper and titanium, and the mixed copper zinc oxide. Another role was the preparation of powder-based feedstock suitable for plasma spraying, and moreover, also the development of the coating deposition procedure, first via suspension plasma spraying, and afterwards with the atmospheric plasma spraying. And finally, they are also involved in the production of prototype antimicrobial plasma spray coating for testing within the project. Next up, we have also the industrial research centers such as IDENER, TAKIS, and CSM. IDENER is a private research company composed of a team of researchers within a sound scientific background in disciplines comprising the branch of system engineering, such as electronic computer system integration and control and process engineering. And we can see here the group that made Miria possible. I would like to thank, of course, Dr. Alejandra Pita, Dr. Patricia Oya, Dr. Ignacio Fernandez Pacheco, Dr. Israel Bevanato, Dr. Cristina Cascares, Dr. Arturo Hernandez, and Dr. Luis Manuel Nunez. Within Miria, outside of Miria, they aim to create new, better, sustainable technologies and business models to ultimately contribute to human development. Next up, we have also Takis, which is an Italian biotech company. We will see tomorrow, we will visit their laboratories. And they are specialized in developing breakthrough immunotherapies for infectious disease and oncology fields. And I would like to thank their team, the CEO Lydia Risicchio, Dr. Laura Riberto, Dr. Erika Salvatore, and Dr. Grazia Vitaliano. And specifically in the Miria project, they are focused on evaluating the antiviral properties of nanoprotein developed by project partners. Next up, we have Rina. Rina, yes. AI is research and innovation for the sustainable future. We are the coordinator of the project, but also we have developed some of the nanoproteins collaborating with some of you, especially with IMM, because we have incorporated their nanopowders into nanoparticles, into our coatings with great results. There are several CSM sites. You can see them all through Italy, and you can see the picture of us traveling through Italy to eat all of them. Just here. Okay, next we have the coating producers such as Protect, Elionadia, and Miria. We have here you can see Miridine team. They are a Finnish company and which develops and provides coating materials for several industrial sectors. And within the project, they had two main tasks. One was to develop antimicrobial coating structures such as matrices with sol-gel and sol-gel hybrids and water-based coatings using antimicrobial nanoparticles provided by the project partners such as VTT. Developed coating structures show the strong antimicrobial effect. We will see that in a moment. And the second goal was to upscale VTT tandem nanoparticle manufacturing process from the lab scale to the next level, where 50 liters of tandem solution can be manufactured. About this, there will be a specific, I do not like to make a lot of spoilers about this, but I would like to thank all the team. Also, we have the area media team. I would like to thank all of them, starting from Dr. Olga Jeremias, and then we have, of course, Dr. Bartolomeo Pawlowski, Dr. Anna Blasica, Dr. Anna Pluta, Dr. Agata Sara, Dr. Isabella from administration, Bartolomeo from marketing, and Dr. Wojciech Mikhail and Dr. Piotr Sobik. Finally, we have also the project. They were founded in 1996. The complete name is Product Surface Technologies, and they were established as a leader in the field of high-vacuum deposition systems, specializing in both physical vapor deposition, and plasma-enhanced chemical vapor deposition. They are located in Belizzola, and their headquarters serve as a hub for innovation and excellence. With almost 3 decades of experience, the company has consistently pushed for the boundaries of surface coating technologies, delivering advanced solutions that cater to a diverse range of industries. And within Miria, they have developed very promising antimicrobial PVD coatings on metal and on metal, basically. Yeah, this is a spoiler also. Okay, and finally we have the end users. Without them, most of our job basically wouldn't stand. So I would like to thank Submetal, Alvo, and Cellphone. I would like to thank first of all, second, because I cannot show a slide. I received it too late. I'm sorry about that, but I would like to talk about it. They also are involved in the textile coatings. And more about it, there will be the presentation by VPT, because there was a journey about the textile coatings that we finally have reached a promising end. I'd like to thank Submetal. They have, their company has over 280 employees and is represented on almost all continents of the world. As an independent family business, it is one of the market leaders in the German-speaking countries with the product ranges fittings, glass, and metal construction. And specifically, I would like to thank Dr. Evelyn Kesslinger and Dr. Nicola Rettensteiner. I hope not to have messed with the surnames of the pronunciation. Okay. Sorry, I forgot to read that. It's a leading company specialized in the development, production, and distribution of high-quality fittings for doors and windows, access control solution, and semi-finished and finished parts for the metal construction sector, with a wide range of products made of stainless steel, brass, aluminum, and wrought iron. Metal successfully meets the needs for the market. With a strong focus on quality and innovation, Submetal will continue to be a driving force in the industry and successfully meet the needs for trade, commerce, and industry. Finally, Albert, which is probably the biggest puzzle piece in the design of the product, because in the end, as Mario recalls, everything was we had an idea, and this idea was basically lighted up some way in our heads when Aldo proposed a specific business case, but more on this will be presented by Alexandra. I would like to thank them. The group is very small, and the picture of the group is very small. The group is not. You cannot see them well, but you can meet them in person here. Medica was established in 1993. The company's headquarters is located in Smigel, Poland. This is a Polish manufacturer specializing in hospital equipment as modular hospital room solutions, surgical tables, and furniture for hospitals. Medica's products are not only technologically advanced, but also designed with a keen understanding of the healthcare environment. The Miria project, Medica was responsible for the definition of the requirements for the innovative coding development. Medical facility, which is simulating an operating theater, has been used as a demonstrator to environment with the number of coded components. The goal of the demonstration was to simulate a safer operating theater. Okay, so basically we have all of us here, which have worked within Miria, and as you can understand from what I've said until now, basically we wanted to develop these coatings, and the final goal was exactly that of having the coatings in a real, or simulated in this case, hospital environment such as the operating theater. How that happens? First of all, we needed funds, so it would be bad not to thank the Horizon Europe project fundings, because basically this is where the magic happens, because without funding we cannot do anything. And basically after the COVID pandemic, there were funds specific for avoiding a specific problem, which was the cross-contamination. To do that, basically the research of Horizon Europe allows the reaching. I will talk a bit more about what is this label TRL in a few moments, to reach to link the gap, which is the lab discovery, the lab development, and the market solution. So often people hear about European projects without seeing their real impact, but Horizon Europe exists exactly for this reason, to help scientific discoveries move from lab to technologies which are real in real life, that citizens from EU can basically see and touch. Okay. So yeah, the cross-contamination was the problem about if we, you probably remember from the COVID pandemic the fact that we were asked to wash our hands more frequently in a specific way. And that is also due to the fact that if we leave our microbes around, there might be some surfaces where these microbes can spread to the next person. And these surfaces might be metal, might be polymer, might be textiles, might be glass. And so Miria project addresses basically all of this. I would not like to make spoilers, but basically I'm doing that. Sorry. Because there was some. Okay. So the Miria coatings needed to be multifunctional. So we needed to have them that active against bacteria, against fungi, and against viruses at the same time. This is not an easy task. And specifically, we were asked for a specific virus, which was the SARS-CoV-19. And thank you for the 15 partners. We were able to cover all the chain value, the value chain, sorry, the value chain of the production, starting from modeling to the market, basically within the product. Now, I promised you to say something about that label TRL. TRL is basically the technology readiness level, and it was verified in the aerospace industry and goes from TRL 1, which is basically the idea, and to TRL 9. Just to make you understand better what is this, I will take an example. For instance, we all want, when we go to the summer, maybe we splash some water on our cell phone. We do not want the cell phone to be destroyed or the files inside to be lost. So one idea might be to have an basically an hydrophobic coating against water to avoid the problem. So the first is the idea. We found some surface, some mechanism that works against water. Then we try to transfer it into the lab on small scale. So we're talking, for instance, at year 3, this is what is called an experimental proof of concept, to transfer the idea on a real object, even though it is very, very small. Then we need to validate that into the laboratory scale. So an early prototype, for instance, can be produced, and then we need to validate it in a relevant environment, and to move from tier 5 to tier 6 means to move from a relevant environment, which might be very, very simulated, very, very not complete, to a real environment. And this in the project area was done basically at the Algo facility now at the end of the project. So without further ado, I'd like again to thank all of you present and other people who are participating in the project Miria for being basically at the end of the project. And I'd like to leave the floor to Aldo for the business case study.
So Polish manufacturing specializing in hospitalizing solutions, surgical pages, and provision for hospitals. So as you can see on the photography, this operating theater is a very complex environment where we have a number of high traffic objects and components that are made of different materials. They are having very complex shapes. So for us, who are the representative of end user, It is very important to prevent the cross-contamination that can lead to the spread of infections. In this interesting project, Miria project, Alba Medical is a leader of more package care. In our facility, which is simulating an operating theater, it was used as demonstrator of the environment in several components. So I will talk right now about the objective of package care. So the main objective of package care is the definition of the requirement for the innovative protein development. We had two objectives, which were the first one is defining the requirements. So this first slide where I was trying to show how this the real environment. So on the photography, you can see the shadow like an album of the people. Trying to say that we got shape, so it's very important to prevent the cross contamination because it can spread to the other. So the first objective was to define shape. So our first task was to show the environment. So together with the she got the we are aware of how business task. Show the specification of the substrates. So the objective was this task was to define the specification of the substrates. Discussed about the environment, all the parts which are available. So we identified the initial 27 candidates for discussions. But of course, this number of samples was impossible to test, so we decided to define four classes of materials, which was glass, polymer, metal, and textile. And inside those classes, we had defined a couple of components which will be tested in the next phases of the project. So it was the touch screen, the surgical display, but also the part of modular whole system, which is another important part of the project. Then we have some smaller parts which are differently touched by the users. right operating program. That's the activation level for the part of the operating table. Also, the handset, which is used for adjustment of parts in the operating table. The side panel, which is also placed in the operating table. The belt, which is used for positioning the patient in the table. But also the metal parts, which are covering the whole operating table, which is based on the whole covering the let's say the first one, the door handle from Signature, also the textile parts, so like tickets for the website, extension, extras, extension. So the result of this, the renewable is the table which contains the software. After our working, so demonstrated the environment. It's very exciting to see after a couple of months of the project that I see the surfaces, the clinical all parts of our operating field, and proceed with the evaluation done on January this year.
Summer, yeah.
Just Testing. Georgia. And the second slide.
Hello? Hello? It's tested from someone, but not us. It's speaking from someone. Okay, the microphone looks like that. Yeah. See your microphone. This is recorded, but not see. It's not. It's let's wait to see. See something.
And now close. Okay, let's try this. Yeah, I know.
Okay, try.
Oh, okay.
Try again.
Now she said now, so better. Now better. So now it's working.
But it's not then try.
That could be also that it goes later. Yeah.
Okay, perfect. Sorry for the interruption. And go on. And you have two microphones basically.
Yeah, this one works.
One from here. Otherwise, we can use that one.
No,
So you have the same direction. Yeah.
this one.
Yeah.
Yes.
So you know that the microphone is from this side. Works? Yes. Okay. So basically you have this one for us and this one for.
Okay.
Like you have
This
to,
one.
yes. To confuse you a little bit more. Yes.
What is it happening to me?
I don't know. I don't know. Oh, yeah, I don't know, but we can find solution for every problem. Yeah. This is the, okay.
Okay, where was I? Yes, so the second cell line was human keratinocyte. Because can you hear me? Because these cells are main epidermal cells, and they are models for cutaneous exposure, which obviously is the main route of exposure when we're talking about coatings. Okay, so the protocol that was used for cell viability was to bring into contact the cells with the particles, and after 24 hours, after 1 day of incubation, the cells that were still viable could be read by a colorimetry test.
Yeah, no,
This one.
Yes. Okay.
Okay. So here's the picture of what it looks like with the positive control, so the cells that are fully viable, and the negative control where the cells have died. And so in between you have all the different colors that are directly related to in correlation with the percentage of cells that die. So the results here, I'm not going into details again, but you have here the results on the murine macrophages and on human keratinocytes of the two methods that were used, cell viability, inflammatory response. So what we see basically is that there's a lot of green in the table, so which means that there was poor or no acute toxicity of the nanoparticles, and also no significant pro-inflammatory effect, except for the copper oxide, zinc oxide nanoparticles. And this was due to the fact that zinc oxide is known to be very toxic. Okay, so the second pillar was functionality. And so for the tests that were performed on functionality, just to remember, the target in Miria was to reduce the infectivity of the pathogens by 99.99%. And this was done by antimicrobial, antiviral efficacy testing. And there was also specific test that was designed to measure the pathogen adhesion on the surface. So for the classical antimicrobial efficacy, the protocol was to deposit a droplet of pathogen solution, pathogen suspension, on either the coated substrate, so the biocidal surface, and the substrate, which was the reference, and to incubate these for a certain time and a certain temperature. And after this incubation, the pathogens were collected in a growth medium, and they were cultured on an agar plate so that the colonies could develop from the still living organisms, and they were counted. The bacteria that were chosen were gram-negative Escherichia coli, gram-positive Staphylococcus aureus, and the methicillin-resistant Staphylococcus aureus. And for fungi, the Candida auris was selected as the yeast. It's an emerging fungal and a critical priority pathogen, according to the World Health Organization. And also a mold, Aspergillus niger, was tested. Now, concerning the viruses, another step was needed to check if the viruses could still infect cells or if they did not have any infectious property. So the infectivity test was performed on epithelial cells, and the infected cells could be identified, measured by fluorescence, because the virus that was chosen was a green fluorescent protein modified adenovirus. Here you can see the example, the illustration of the test that was performed on bacteria. The microbes here on the top image are deposited on the samples, the square samples, and they were incubated. And after the collection, you can see the bacterial colonies that had grown. Here, there are these dots on the agar plate. So an example of what was obtained in Miria. Here you have the antimicrobial activity for different type of samples. So mainly there are silver or silver-based paint coatings on various substrates. So three conclusions here is that we have good to very good antibacterial activity. You can see that they are, so the orange bars, orange and Yes, and brown bars. There are over 99% of activity. But there is lower efficacy against the Aspergillus niger, the fungi. So fungi is this fungi actually is more resistant to this type of coating. But what's interesting also is the improved efficacy. If I can... No. It's the improved...
to have them. Okay.
Yes. What's interesting here, yes, is the improved efficacy between the pure silver coating and the coating which was added other nanoparticles, other metal-based nanoparticles. You can see that that was with these composites, the efficacy was much higher, significantly higher. Another illustration concerning the viruses. Here you can see that the fluorescence expression of the cells that were infected by the GFP adenovirus. And similarly to the previous tests that were performed on bacteria and fungi, here you can see the viral reduction for the same samples. And so the main conclusions here concerning viruses is that the antiviral efficacy is lower compared to the antibacterial efficacy. So viruses are more resistant. The antiviral activity was also confirmed for coatings on metal. So here it was aluminum, and there possibly a synergistic effect between the aluminum substrate and the metal, the silver coatings, the silver metal of the coating. And what's interesting too is the fact that the biocidal activity is fast. There is fast kinetics. You can see here after only 1 hour of contact that we already have antiviral activity. Okay, so the last pillar was durability. Some mechanical tests were performed to have the basic information on the substrates. So profilometry, AFM was performed to have the roughness, the thickness too, and nanoindentation to have the hardness and elastic modulus. Some wear tests were performed to have the wear coefficient, and scratch tests were performed for the critical loads. So these are very interesting parameters to have information on the cohesion of the coating and also on the adhesion of the coating onto the substrate. Some additional tests were also performed. So for example, chemical weathering was performed on hard surfaces by wet wiping the surface with a disinfectant cloth. So this was done to mimic the cleaning procedures that are performed in carried out in hospitals. And we also have the accelerated aging by controlled irradiance, temperature, and humidity. And of course, the surfaces needed to be characterized before and after these tests to check if everything was fine or if there was some alteration of the surface. So an example of the surface characterization with roughness. So this is an example with the sol-gel coating that contains copper oxide nanoparticles, and it was deposited on a glass surface. And you can see a very smooth surface actually, because the roughness was in the order of a few nanometers. And what you can also see here is the little spikes that correspond to that point out of the layer that correspond to the copper oxide particles. And it's a very interesting feature in the sense that they are directly in contact with the pathogens. So this type of coating was interesting, particularly because it's very thin, it's very smooth, and it's also transparent. So for touch screens, for example, it's a good solution. An example of scratch test results here on the TRL5 samples. So basically, we can see that the samples fall into 3 different groups of mechanical resistance. There is the group with poor resistance here, which is basically the polymer substrates, all types of coatings on polymer substrate. Then there's a good group, which is made of sol gel coatings and paint on metal, and the very good, those that perform very good concerning cohesive and adhesive resistance, which are PVD, physical vapor deposition, so on metal, and paint on glass. Then finally, an example of the wet wiping test that was performed here on one of the first samples that was sent, that was produced and sent to CEA, which is a PMMA coated sample with a silver paint coating. You can see that after the certain number of cycles, the coating was wrapped off. And this could be monitored by measuring the silver surface concentration by X-ray fluorescence. And here you can we can quantify the decrease of the silver concentration. And what's interesting here is that the same experiment was performed, but with a dry wipe, and actually there was preservation of the coating. So here we can see that the predominant role in the alteration of the surface was the disinfectant solution. So this information was sent to the producer of this coating, of this sample, and so the partner changed the substrate and also the coating deposition process, improved the deposition process, and this led to a good resistance to the wet wiping. Okay, so last, this is a table of the results. I'm not going to discuss it, just to point out that there was a lot of green dots in this, meaning that the tests had passed, and that most of the samples were upscaled to TRL6 to the demonstration phase. So the last slide, we performed tests on 13 nanoparticles for toxicity, and 80 technical solutions were tested. And from these, 9 coatings were selected. 13 technical solutions were then tested from these 9 coatings, and 8 technical solutions were then selected at TRL5. And they were applied on selected components and objects in the demonstration phase. And so if you want to go to know more about these results, one paper was accepted, so it will soon be released in Nanomaterials, and some other papers are in preparation that you will possibly see in the next future. And I thank you for your attention.
Thank you.
Sylvie. Now I think that we can move on to Daryl for developing. Your turn.
Hello?
Okay. I don't know if
Amen.
Yes.
yeah.
Yes, if you want.
Presentation mode.
Okay. Thank you very much. So I have to talk to this mic, look into this, and change.
Move there.
Okay, perfetto. Buongiorno tutti. Hello, everybody. We from IMN work in leadership of work package 4, which was focused on the development of coatings. And in fact, we have heard already some information about the properties of the products generated in the project, but now we have to come back to the antediluvian times when there was no nano coatings, there was no nano powders, there was only just 4 elements and us to develop the work, and we started with with the idea to work on the development of nano coatings, and the order of things was to design the nano coatings, how we would like them to look like and operate. We have to develop a process of production of nano powders that we can incorporate in the coatings, and then develop the nano coatings with a variety of approaches presented by the partners. In fact, in the work package 4, almost all the project partners were involved. And at the same time, we also wanted to develop a model for the coatings. So it was a task that was carried out in the same work package. So to design the coatings, we combined the expertise from several groups of people. So we had experts in antimicrobial materials. We have experts in production of nanopowders, also expert in production of nano coatings, and all this information has to be combined and implemented in a pilot scale studies, so we can produce effective nano coating of the properties that has to be tested and confirmed of its applicability. And our target was to have 10 candidate coatings at the end of our activity. And the first step was development of nano powders. We had several approaches. We had several materials that we would like to work with, and there was a large group of metal-based materials, mostly working in silver-based materials, also copper oxide, titanium, zinc oxide. These were the metals that were considered in the production of the nano powders, with the special care for their antimicrobial potential, for the implementation. And the development of the powders involved, of course, complete characterization of the powders from the point of view of their physical properties, and of course the toxicity that was mentioned by Sylvia already, that was tested. And as I said, they were metal-based, but we had also approaches for implementation of other nanomaterials in our products. So light-activated nanoparticles was one of the exciting areas of implementation. So nano polar photosynthesizers with upconverting nanoparticles. That was one of the targets, and produced quite interesting results. And the bio-based nanoparticles, which were tannins produced from a spruce bark, for implementation in the textiles at the end of the day. So that was quite interesting also target. And that was the whole list of the nanomaterials that we developed and then tested for the application. So as you can see, the metal-based materials, copper, titanium oxide, copper oxide, also silver-based. There was also one of the materials where we implemented graphene and nano silver, micro silver applications, as I said, light activated composite polystyrene nanoparticles based on sulfonated polystyrene nanoparticles, and also tannin nanoparticles. What we wanted to achieve was also some potential the production of each of them. So we don't just produce very tiny bits of the material, but we wanted to have at least a volume of 100 grams produced per month, so we can use the materials in the nano coatings development. So once we had this nanomaterials ready, we could move to nano coating development. And just like with the nanomaterials, where we had a variety of the materials that we work with, we also had a whole range of technologies for application. There was suspension plasma spraying. There was also atomic plasma spraying, which was tested, foam coating. There was social techniques, bar coating, deep coating, wipe coating, physical vapor deposition, also printing and painting using aerodynamic spray as the method for coating development. So whole range. And also, as I mentioned before, a large group of nanomaterials which can be implemented. Of course, not all of them were suitable for all the techniques. But we also had four substrates for application of the coating. So we had to test possibilities of specific applications using specific techniques. And as I just a shortly a review of the coatings. So bio-based coatings where we use tannin nanoparticles. Here the foaming process was used for application to textiles. That was in fact the most interesting candidate for textile application, which is quite challenging method for or substrate for application of the coatings. Then we move to suspension plasma spray, where we use metal-based, mostly copper-based coatings with copper oxide, and a combination of copper oxide and zinc oxide, copper oxide and titanium. And also subcoating application was tested in the development of the nano coating. The next group of the coatings was related to paints, and here we use nano coatings, nanoparticles, silver-based nanoparticles, and we are able to come up with coatings for metal, for glass, but also on plastic. There was a different of course nanomaterial used here. And a group of social coatings, which was also quite successful. We had here inorganic coatings and incorporation of nanoparticles produced by partners. Here Rina was leading the way, but also using other partners nanomaterials. And the coatings were tested for application to glass, to metals and polymers. And the group of physical vapor deposition coatings were ceramic materials were introduced, chromium carbonitride and titanium nitride. Also interlayers were tested for improvement of adhesion of this coatings. So in the result, we were able to produce nine coatings, two using SPS technique, 2 coatings using PVD technique, 3 with the sol gel, and the 2 coatings silver base in a paint form. These were according to the targets that we established, and we followed them. I have no information about the results here. That was shortly presented by Susie also. And as I mentioned, we had also task focus on modeling. There were two areas of modeling that were developed in this work package. So it was molecular modeling. So we wanted to create a molecular dynamic model to describe the interaction between the pathogens and the surface of the coating. So collection of information, then building up of the numerical model. So we are able to present mechanical forces, chemical interaction stresses in the interactions under different conditions. So this is how it looked like with in practice. So after calibration of the cell fluid coupling and cell parameters, there was construction of the model based on the surface data and a simulation of the deposition based on the information gathered from the partners who were developing the techniques. And implementation of pathogens of 3 types, definition of interactions in the models. And the second modeling was focused on the energy consumption. So collection of information about the different processes used in the nanocoating development and manufacturing processes. So thanks to the energy modeling, we're able to learn what are the energy parameters related to the process, also raw materials consumption and the final products. So we are able to identify the most energy consuming places in the specific processes. So this is the example that we can see of one of the coating technologies, sol gel nano coating process, where all the information were collected about the energy consumption for the processes and operations. And this provided feedback to the partners who are developing the processes, so they can maybe intervene somehow in the process, so make it less energy consuming and more energy efficient at the end of the day. And in fact, it was done by the partners here. So to sum up the work package 4, as I said, there were experimental studies for development of nanoparticles and the nano coating development, and we reached the target of development of relevant number of efficient coatings. And at the same time, this was the simulation and modeling, molecular and energy modeling. So we were able to have fundamental models, which were then developed in work package 5, also for practical applications. So we were able to produce the products in the form of nanocoatings with the required antibacterial, antiviral, antifungal, and also mechanical properties, which were very important because this is not just antimicrobial, but all this requirement for the coatings had to be met, and we were able to address all the relevant substrates, which was glass, plastic, metal, and textile, and were able to select the most promising candidates for upscaling in the work package 5. So I'd like to thank you for the attention. I'd like to thank all the partners in work package 4. It was really fantastic work done together, and the cooperation was really great. And thanks to the coordinating team. Thank you.
myself. Okay. Okay, after the upscaling to TRL4, we moved to a validation in a relevant environment. So by upscaling the antimicrobial coatings to TRL5. So as we saw in the beginning in Angelo's presentation, this is a brief description of how we work with TRL and especially the meaning of TRL5. So it means that a validation to a relevant environment. And so this is a focus on how on the meaning of validation to TRL5 for coding in particular. So all the coding technologies will be validated in a representative environment to tend to the final application. So the key technical performance and functionality were demonstrated by providing confidence in the technology potential. So we divided the assessment of the nano coatings obtained in the Miria project in 6 different steps. So we can see a molecular modeling, a relevant environment testing, the performance validation of each coating, the prototype coating system. So moving to a more lab scale technology to more industrial one. We also managed with the reproducibility, of each coating with the maintaining of the characteristics, moving to the demonstration at TRL6. So for the molecular modeling, it was performed by the partner Edener. So the steps to optimize the model was to study the position of pathogen in antipathogenic substrate, considering the stress endured by deposited pathogens on the cells, an indicator of the antipathogenic characteristic on the surface. In particular, they characterized the role of the substrate geometry and the effectiveness of the nanocoating surfaces, and also by increasing the number of pathogens modeled for this reason, moving by the SARS-CoV-2 to any other case, in particular Staphylococcus aureus. So, okay, the video is working. So the partner achieved the objective described in the previous slide by delivering the analysis of parametric variation of the substrate geometry and providing the explanation of the role of the roughness and the dispersion of the deposition process. So by establishing a relation between the contact area between the cells and the substrate and the stress endured by the pathogens. So another aspect of the modeling was about the energy and the mass analysis by focusing on the manufacturing process of different coating technology. So the main goal was to analyze and optimize the upscaling of the nanocoating production by redefining the some flow diagrams and evaluating characteristics such the energy consumption and the mass flow to TRL5. So this was made by close collaboration with all the partners and by filling some technical data sheet that were taking into account the mass balance, the energy balance the consistency, so allowed us to obtain detailed analysis of the nanocoating manufacturing process by identifying opportunity to optimize the process also for future upscaling. So for the nanomaterials and the nanocoating production, we can see we can divide the aspect for the process concerning the nanoparticles production to the ones concerning the nanocoating process. So basically, we identified different kind of nanoparticles, such as copper oxide powder, copper oxide based particles, silver based, or tannin or light activated. For the nanocoating process, we consider APS, the paints, the sol gel coating development, the PVD, and the bio-based coating. So for the production of nanoparticles of copper oxide nanoparticles, the task goal was to improve the production capacity of the powder, going from a bigger amount of monthly production. And this was obtained by switching from the suspension plasma spray technique to the IPS technique. So this allowed to optimize the production process. Also for the silver nanoparticle, the optimization and the increase of the production was mainly focused on the while maintaining also the quality and the safety of the obtaining of the process was obtained by increasing the number of furnaces dedicated to the production of the materials, and also by increasing the reactor volume and optimizing the process. So for tannin nanoparticles, the scale up was to the task goal predicted to have a water-based solvent-free dispersion for antimicrobial textile coating, specifically to obtain foam coating. So the activities performed were based on the remodeling of the process by dividing it in 4 phases: preparation, filtering, nanoparticle formation, solvent removal, but also the key development wants to insert a sonicating process to improve the particle size control, and it was integrated in the process. Also for light activated nanoparticles, the goal was to improve their thermal stability, and this was done by was implemented by using new materials, so switching to the original polymer used for the basic research, moving to a new type, and also by optimizing the process. Talking about the coating, the task goal was to optimize the suspension and the spraying parameters. So it was obtained by moving to a different technology for the coating. So moving from suspension plasma spray to atmospheric plasma spray. So the coating obtained was thicker and denser, and better adhered to the surface with and less porous. So it achieved excellent performances in the antimicrobial and antiviral reduction. Also by improving the mechanical durability, and the process was completely reproducible. For the paint, the task goal was to transition to from a laboratory to pre-industrial scale by enhancing the production efficiency and by validating the performances on metal, glass, and different substrates. So the innovation that were done in to reach the TRL5 was to improve the batch size to obtain more of the product, and also to the coating obtained were excellent with the addition, and the performances from a biocidal point of view were really high, reaching more than the 96%. So for the sol gel coating, the task goal was to transition to deposition method that were more on the lab scale to more industrial relevant deep coating on a larger substrate. So the technology transfer was successful, and the coating obtained were improved in terms of uniformity and reproducibility. So for the PVD coating, the process was already reproducible and creating durable and antimicrobial surfaces on steel and polymer surface. Sorry, but the activity were focused on the upscaling strategies to where to obtain to perfect some of the critical aspect processes, such as the deposition time. And for the bio-based coating, the main goal was to move from health textile also to food and safety, and to develop antimicrobial food absorber to reduce the waste, and to focus on natural tannin nano-based solution. So the tannin nanoparticles were applied to cell comb absorbing pads. The process was improved by modifying the drying method to impact on the coating structure and its effectiveness. So this is a table that resumes the thing that we do for the validation at the TRL6, and how each coating the substrate that we considered for each type of coating, and I mean the pass on the antimicrobial efficacy, and for TRL5 we obtained the milestone of the validation was to obtain at least 4 coating solution validated at TRL5. We obtained 6 coating solution validated at TRL5. So thank you for your attention, and I would like to thank all the partners that work on this validation at TRL5. So I think that we can move to TRL6. So I don't know where to find the presentation. Page. Qualcuno? Non lo trovo. Questo clicca. Ok. Qua? Oh, sbagliato. Okay. Oh. Which one? I think it's this one.
Yeah, it's that.
Okay.
Yeah, and then I need to have the
laser here. Yes, this one. The first
one.
Yes.
Okay. Yes, hello everyone. Still a bit to go. So I'm Malin Bomberg from VTT. I've been leading the VP6, and it's been a very interesting interesting work package, to say the least. So let's jump into the reasons for this whole project. Angela already gave a very good overview of why this project is exists. And just as a for everyone to think about, we are actually just transport vessels for microorganisms. Every fingerprint that you leave behind contains maybe 1 million bacterial cells. So that's quite a lot of stuff we leave around. And some of those microbes can be pathogenic or bad for us. This doesn't mean that all these millions and billions and trillions of microbes that we have on us and in us are bad for us. Actually, most of them are very important, so we wouldn't really survive without them. But then there are the pathogens that make things difficult. And in hospitals where we get to go to get better from disease or from accidents or so, we would expect that we don't get any infections, but that might not be the case. So surgical site infections are one of the most common types of healthcare associated infections that can affect anyone going into some kind of operation or hospital care. And the most common sites of surgical sites infections are hip and knee prosthetics and cesarean sections. And anybody can understand that that's not a good thing. And then there are, of course, all kinds of other surgeries or applications from where things can happen. And just as a reference, there are several surveys and studies being done over the years, but in one survey from 2018 to 2020, not from each and every hospital in the world, but from a certain set of hospitals, they reported 1.26 million procedures, from which 20,000 1.26 million procedures resulted in an infection from the hospital, and 20,000 of those were surgical site infections. So that's quite a significant number. And also another survey reported 3.8 million patients that had got at least one hospital-associated infection. And many of those had more than one infection that they had got from their visit at the hospital. There are a lot of different microorganisms found that in these different hospital-associated infections, and the most common ones are the E. coli and S. aureus that we have been working with also here in Miria, but there are, of course, many others, and there are fungi and viruses and yeasts and all kinds of things. What you see here on the picture, these small dots, if you're not familiar, these are the colonies that are formed from one bacterial cell. And this is what they look like when they are grown on the agar plates that we have been using. And this is how they can be counted.
No, yeah.
This one.
Yeah.
So where do these microbes come from? Well, the patients and the staff healthcare personnel and other staff are already, as I said, we are the vehicles for transporting microbes around. And they also come from visitors and contaminated objects and surfaces. They are transferred by just from hand to hand or from different surfaces. And there is a clear transport or contamination chain going, for instance, from the door handle to the hands of the person touching the door handle, to the equipment, and from there onto the patient. And just using gloves does not stop this transfer. If the glove touches the contaminated handle, then of course the glove will spread this microbe further. How much of these microbes are spread per touch is up for debate. There are reports that only maybe a few percent from the fingerprints left on a surface, up to 85% of the microbes are transferred to the next surface. And the more surfaces a person touches with the contaminated hands, the further the contamination spreads, and then we have a network of contaminated surfaces. What could help to slow down this contamination and spread of pathogens from surfaces is to have an awareness of the network that we are creating with these contaminations and the microbes, and the proper hand hygiene that was already mentioned by Angelo. Also surface cleanliness and disinfection. And then what we have been doing here with the antimicrobial coatings, if they are kept clean, they would also be very efficient to break this contamination chain. Again, this is too complicated. So the point with the antimicrobial surfaces and coatings is that the microbes that survive on the surfaces decrease significantly. And that would then also decrease the hospital-associated infections. And all the different nanocoatings that we have tested in Miria has already been shown several times. But I think that this picture shows very clearly how the different coating variants that we have been using, what they look like on the same object. And here we have the Sydmetal door handle as the example. Right now. The goals for the work package 6 was to design the testings and design the protocols for assessing antimicrobial activity of hospital surfaces in a real life environment. We did testings in controlled laboratory conditions with real pathogenic microorganisms, and here the goal was to see a 99.99% decrease in microbial survival on the surfaces that had an antimicrobial nanocoatings. But going out into the real world is a bit different. First of all, we cannot take the pathogenic microorganisms out of the lab because of, well, security reasons. and the hazard that people might get infected, and especially in Alvo's theater. So we tested and compared the same protocols with non-pathogenic safe microbial strains that could be transported. Another difference here is that the absolutely same procedures for lifting the samples from the surfaces and detecting the microorganisms as were applied in the laboratory conditions cannot be applied in real world scenarios, because there is not the needed equipment and time to do all the steps that we need in order to show the 99.99% decrease. But since we already know from laboratory tests that we can reach these levels in the controlled environment, then using a 90%, over 90% decrease in microbial survival in real world scenarios would be a proof of concept that this still works in the actual environment. Well, we had the test objects. They were metal, plastic, glass, and textiles. And this has been said many times today. And I want to dive directly into the visit to Alvo's theater. So in the field, here is Satu preparing the microbial mixture and the application of microorganisms on the surfaces. So we used this paint roller that was filled with microbial mixture that we then rolled over the surfaces to apply the microbes, and on different surfaces we have here the side panel, I think. This resulted then in the objects with the microbial coating on. I don't know whether you see it very clearly here, but this handle has a second coating of microbial mixture, and also this piece of glass here. I see it very well here on the screen, but it might be a bit difficult to see on the big screen. And the sampling then, or the lifting of the microbes, happened like this. So we have this very thin so-called Petri film, which is this kind of, where am I? Very thin sheet that contains the microbial growth substrate here between two plastic, thin plastic pieces. And this growth substrate can be pressed to the surfaces like this. And now all the microbes that are on the surfaces are transferred to this growth substrate. And then we have a whole lot of these playing card sized samples for to assess then the antimicrobial efficacy of the surface. We might also have these petri dishes with bacterial colony growth, and here we have a picture of how the viruses are detected. So in the field, not at Alvo's facility, but in the field. So we have a small plate coated with or covered with a bacterium, and all these spots that you see here are from one virus particle that has infected its bacterial host, and And while the bacterium is still growing a bit, well, when it is growing the virus inside it, it spreads to form a small sphere on this plate. And then when the virus is released from the bacterial cells, they form this clear spot called a plaque on the plate. And then we have all kinds of beautifully colored different microorganisms that we can detect. And going to the results for the 3D objects. The missing numbers here are from tests that gave a result with less than 90% efficacy in the field. So that's why they are not shown. They have all been tested. The adenovirus was only tested in laboratory conditions, but all these other tests were run both in Alvo's operating theater as well as in the laboratory at VTT. These show quite promising results, but these have been these are the best ones that I chose here. So all tests were run 3 times for every object in at VTT and in Alvo. And the repeatability of these tests were not always as good as it would show here. But we know that we have results showing these tests showing these very promising results. Just to mention that these are all the metal, glass, and plastic or polymer samples that we tested, and now let's get to the tannins as antimicrobial agents. Tannins are a diverse group of very complex molecules that are extracted from plant bark. Plants produce these tannins as a protection from herbivores or pests and all kinds of microorganisms, and they have naturally antimicrobial properties that inhibit the growth of fungi and bacteria in the forest, for instance. When we think about the spruce and pine trees that we used here in this study. And they are especially common in bark because this is the first line of defense against insects and pathogens that the trees can produce. There are a lot of different types of tannins, but let's not go into those details. The important ones here are the spruce and pine barks, or tannins from the spruce and pine barks, and that's something we have locally in Finland quite a lot. So here we set out to treat some non-woven viscose based textiles from Cellcom. And you already saw these pictures, but here they're a bit bigger. Here the surface is treated with, it was some kind of corona treatment. I cannot give you more information about that, but this was done at VTT. And then here we have the application of the nanotannin foam. So it was not sprayed on, it was the nanotannins were mixed into a foam and spread on top of the sheets. And here you see you see what the tannins look like before they become foam. Several different strengths of tannins were tested, and this is wet when it's when the tannins are applied, or the foam is applied. So it needs to be dried, and VTT tried drying at room temperature overnight or at 105 degrees for 5 minutes. And here we go to the pilot scale, where we have this patient transfer sheet coming out of the foam applicator. And here it is dried under an infrared dryer. And also the adjustment of the drying was quite critical, because if it was dried too fast, this wrinkled up the sheet quite a lot, and this is not usable. But when it was dried properly, then it stayed flat and nice. Something more about the drying. So when the nanotannins were dried at the higher temperature, they fused together and formed this kind of sheet of nanoparticles that, or you can't really see the nanoparticles here from this film. When it was dried at room temperature, you still see the separate nanoparticles here, and then it started to crack, and the result from the drying was just different using these two different techniques. Interestingly, this film had higher antimicrobial efficacy than this room temperature dried version. And here we reached efficacies of more than 99.99% against the Staphylococcus aureus, and also almost reached the 99.99 against the E. coli. Well, so it was a bit lower, and these nanotannins were also effective against the yeast Candida. And we had an opportunity to do virus testings on different coatings and base materials also when Jana went for a research visit to the University of Jyväskylä last summer. And you cannot read these, but we have silver coated and copper oxide coated metals and some plastics, and then we have the nanotannin coated transfer sheet pieces, and what was clear from the tests were that both with the non-pathogenic Phi6 bacteriophage that we also used in Alvo's facilities, and then the seasonal coronavirus that is a real pathogen in both cases, the nanotannins were effective against these viruses. So to quickly try to sum up the work package, the transfer chain of pathogens from surfaces to hands to patients is a major driver of infection risks in hospitals and surgical theaters. And to reach a high level of decrease in hospital transferred infections, there is probably a need to have layered controls, such as, well, the hand washing and hospital surface hygiene in general, and then the nano-coated, the antimicrobial coatings, and very good cleaning in between all these barriers. Because if you have, even if when we have the antimicrobial coatings, if there is a buildup of biomass and microbes and things on those, then the antimicrobial efficacy will not reach the outermost layers of the freshest microbes that are applied to the surfaces. But we have seen from all our tests that the coatings can significantly reduce the viable microbes on high-touch surfaces. We also, through this journey with the nanotannins, have found that they have a strong antimicrobial efficacy, and they might be a good option for textiles, as they are bio-based. They would be quite reproducible. Finally, that multiple protein systems can be adapted across common hospital surfaces and practices. And this is just a summary in a more graphical way. So I thank you for your attention.
The next one.
So I think our next speaker is Michelangelo. Imparato. Okay.
Right, yours. Hello, everybody. I'm Michelangelo Vailardi from Protec, and I'm here to explain the work carried out during this 4th year of the project in the work package 7 that is related to the exploitation strategy definition. So here just a slide with the summary of what we are going to see in the slides, in the next slide. So first overview of the work package, an overview of all the tasks of the work package 7, so task 7.1, 7.2, 3, and at the end of the deliverable status. So in this slide, we have just reported the objective of the work package 7 that relies into the definition of an exploitation strategy that needs to be addressed with a final deliverable, which contains the business plan, the final business plan of the Miria project, the life cycle assessment, the life cycle cost, and the social life cycle assessment, and of course, the related market analysis. So let's start from the task 7.1, which was mainly related to the market analysis and the business plan development. This is the pathway that we had followed during this 4 year of the project. So we start from the definition of questionnaires and tables to gather new stakeholders into the project and to find the data that we need to apply to a business model, which was selected the Canvas business one, since the customer is on the center of that business model. So we have selected it as the proper one to be used for the project. At the very beginning, we faced some problems in gathering the data and gathering the stakeholders with the questionnaire and the table. So we moved to a more dedicated questionnaires to consolidate the stakeholder and confirm the interest into the project. So we have adapt our strategy during the project to increase the efficiency of the communication and exploitation activities. So here we have just reported the hindrances that we had at the beginning of the project. So lack of response, lack of Miria interest, just because we do not have results to be shared with the possible stakeholders. So we were a little bit stuck at the beginning, but once we had the first results from the work package 4 and 5, we just moved into the activation of workshop, webinar, some publication of paper. And so the plan was to apply, or better, to set this workshop and webinar, which were selected to be at least 5. So one related to the film characterization, to the employee technology, to the microbial modelization on surface, to the sustainability analysis that will be done today, and on the CHADA topic. And all of them were done roughly in the last year of the project. So thanks to this plan, we were able to apply all the information to the Canvas business model. And thanks to also the information gathered from the partner about the updated business plan that was required some months ago to the partners. And right now we have achieved the final business plan. We are 95% ready, just because we need to update the deliverable and to send it to all the partners. Regarding the task 7.2 of leader, here it's still Protec. So the task 7.2, it's related to the IPR and exploitation strategy. This is, let me say, a sum up of the other tasks and the other activities on the project. So in this plan, in the exploitation plan, there will be a sum up of the business plan results, a sum up of the results gathered from the sustainability assessment, and a results of the IPR management. So we start from the first deliverable that was the 7.3, drafted in the months 18. We start to work on that into the following points. So in the evolution of the project, just with an update of the stakeholder identification, with the explanation of how we have to reach the technology readiness level, with an update of the exploitable results, an update, of course, onto the market opportunity with the identification of the key barriers and the opportunity related to all the market identified as the possible market where the coating or the results of the Miria project can be used. The industrialization roadmap from TRL 6 to TRL 9 after the project, so how to get to the technology readiness level, number 9, okay. And so going on here, just an overview of which are the main difference related to the final draft of the exploitation strategy respect to the previous one. So we can just have a look at the business model. At the beginning was identify only the business model to be used, and right now we have a final definition of the business model with a sector-specified canvas populated model. Okay, so in the last task, which is the 7.3, where the project lead, the task leader was Idaner, that have done a really great job during this the project lifetime. This task is related to the sustainability analysis, which is mainly related to the definition of the life cycle assessment, life cycle cost, and the social life cycle assessment. Here they have just reported which is the roadmap followed during the project lifetime. So a definition of the goal and the scope, the data collection from all the partners and from all the value chain, the stakeholder value chain, a preliminary assessment, calculus and analysis of the data, validation with all the partners, and the integration into the final reporting. So in this slide, they have just reported which are the instruments that were used during the project to achieve the sustainability analysis. For example, the Open LCA, Econvent, PS, ILCA, and the European mapping of the end of route procedures, where they were able to follow the procedure and together the information that was missing or that was missed from the partners to achieve the final life cycle assessment. And while in this slide, they have just reported the stakeholder value chain that was considered for the sustainability analysis that was divided into 3 main stages. So at first, the nanoparticle production, then the nanocoating production, and then the end user, which is in this case Alvo. For the LCA and the LCC, they have just considered the first two part of the value chain, so the nanoparticle production and the nanocoating production, while for the social impact assessment, also the end user, with a cradle-to-gate approach, which means that they were able to consider the entire life cycle of the product from the raw material extraction to the processing to the point where the product leaves the factory and before the distribution into the market. Okay, here we start to give you some of the results obtained from Edener with the sustainability assessment. So as first we can have a look on the life cycle assessment, where they have just reported which are the main impact indicators that impact, of course, the life cycle of the product. So, for example, for the coating, nano coating 02, we have the electricity as the main impact indicators, while for the nano coating 03 and 04, silver are the core impact indicators. And for the other 3, so 05, 08, and 09, we have electricity and energy in general that are the main impact indicators. All these data were obtained with some questionnaire that was shared to the stakeholders and to the partners. And so going on, here we have the summary of the life cycle cost results. Here Edener has considered all the costs related to the capital expenditure, operational expenditure, materials, energy, workforce, and maintenance used to create the nanocoating or the nanoparticles. And in the table, they have just reported which are the main economic indicator that affect the cost of the product. So for the nanocoating 02, or better, for all the nanocoating that are reported here, we can see that the operational expenditure are the dominated ones. And in this slide, they have just reported which are the results of the social impact analysis. So on the top, there is a legend bar where the green color represents just that there is no risk in the social indicator. And the red color, of course, represents a very high risk within that social indicator. So they have just subdivided the value change into three main categories. The first one is the nanoparticle production, then there is the nanocoating production, and at the end user, as we have seen at the beginning with the cradle-to-gate approach. We can see that in more general, we have a high amount of green cells. It means that in general, we have just a good social impact, a good social impact, and this good social performance. And this represents a strong social profile with a good potential to be scaled up in the future at the end of the project. Last but not least, they have also evaluated the end-of-life perspective of the value chain. So for the nanocoating and the nanoparticle production, so they have evaluated which are the waste categories for example, the aqueous waste streams, solvent-based waste streams, solid nanoparticle resides, and exhaust gases with their associated selected end-of-life route. And they have also evaluated the end-of-life route of the final components, so of the final demonstrators onto the substrate like glass, metal, and polymer, with their associated end-of-life route like recycling, scrap metal recycling, and yes, in general, we have only recycling as the selected option. So regarding the deliverables, here we can have just a brief look of the deliverable that needs to be charged within the end of this month. So deliver 7.5, 7.6, and 7.7. We are roughly at the 95% of all of them, and we are pretty close to the upload of the deliverable onto the European portal. So thanks for your attention.
Yeah, now it's your turn.
Okay.
We can move to the work package 8.
So, last ride on the final part of this project, everything related to the communication dissemination activities. Well, first of all, what I will discuss right now is I will talk about dissemination strategy, general public, all the research impacts that our project affect over these 4 years, the stakeholder engagement, our commitment in webinars, workshop, and press release, collaboration with similar project, and conclusion. First of all, we have to say the dissemination communication part didn't start, of course, yesterday, but start the first month of this project. So it's something that I want to underline, because to create a good network, we need to work together with the research. And how we created this network, we decided to take a different path, like mass media, which are more direct, or article, website, workshop. And Miria target was different, from students to more research community, stakeholders, of course. So as I said, to talk about dissemination, we have to consider how the project grow over this month and these years. The project is based on 5 milestones. And most of them, of course, are related on development of these coatings, but there is one related to the creation of a stakeholder network. And in particular, this milestone we reached at month 36, indeed, because we created a good network. Okay, So how can we understand how our project was going over this month? There were important KPI to take into account of this period related to general public, policymakers, direct stakeholders, indirect stakeholders, industry or researchers. All this KPI makes us understand if we were moving on the right way and which risk we needed to take into account and how can we improve over time. And we can say proudly that now we have we get all these KPI, or we are nearly close to most of them. Specifically to the general public, we are also over the target. So the strong commitment always prize like this. So first of all, as I said, we decided to take into account a direct channel to connect with our network. So we developed the website and then LinkedIn and YouTube. And thanks to you and to your commitment in reposting, posting, and blah, 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 we reached the good, as I said, the good numbers in the general public over the target suggested in KPI. Then we had the research impact. Of course, together with the general public, there is research and how our partners spread our research activities and our knowledge through Congress presentation, papers, and patent. For the Congress presentation, right now we participate to 18 Congress, most of them international, some other national. These are some pictures just to prove that we have been to this Congress. Then right now we published 5 articles on in different journals with the high index impact, high impact. And the last one on metal oxide was just updated like 2 days ago, so very very close. And most of them are on different topics and included all of you, I mean, Eidner, Charles University, RINA, and I know that some other papers are ongoing. So there is a lot to say about this, even in the coming month. And also there is a patent, which this is involved the cooperation of RINA with IMN. This is based on the sol-gel and copper oxide. And this is an important proof that our research is not just academic, but it can be developed in the industry. It needs to be developed in the industry and the hospitals. Indeed, another important challenge of this project was to engage stakeholders related to the company or hospital. First of all, for the company, we we contact 7 industry right now from different fields like producer of coating, university, or healthcare, and thanks to some forms, we received important feedback from this industry, as industry really interested in our work. So this is something good also for taking into account the hospitals as well. We have different hospitals that decided to sign to our project in Italy, Poland, or Greek to prove that our research was going in a good way and they were really interested in our work. Of course, how we can, what we did to bridge our research and our knowledge, we decided to organize webinars. Right now, there are 4 webinars available online on YouTube. And I mean, it was a good chance for you to spread your knowledge and to increase our network over time. So, then there were also workshops organized. This one is the very early stages of the project in Spain on sol-gel. And another channel that we decided to consider to spread our research are the press release. Even in that case, we are over the target requested from the KPI because our project is being how to say, published in different journals, like 8 journals, local journals. And of course, this project is not just a project related to the research, but also we need to consider that it is an European project. So for us, it's really important to have good connection among partners, but among other projects that has our same topic. So we also, during this period, create good collaboration with sister projects like Susan Project, the Reliance Project. And like 2 days ago, one of our partners take part in this important conference with other important European project that has the same topic, nano coatings topic. Okay. So the conclusion, we can say that the project achieves strong visibility among researchers, industry stakeholders, policymakers, and general public. We reached most of the KPI requested for this project. And of course, even if today is, let's say, our final meeting, this project will go ahead even after this day. So that's it. Thank you.
Thank you, Chiara. So I would like to thank every speaker of today, and of course, every and each one of you for your great work in this project. And I would like to make a round of applause to every speaker of today. That is okay. I will start with this great project. And in about 20 minutes, there will be lunch. And after lunch, there will be the workshop from Idena, and then the visit to the INSTM laboratories.
I also have a video.
Oh, there is a video.
Do you want to see?
Yes.
Right now or after lunch?
No.
Okay. Okay. So just a quick video with some photo over time. Okay. It's working. No. No, but you can. You don't see it. Okay. Cool. Così fa.
Facendo un po' di video.
Condivido qua. Non c'è. Forse qua. No.
Mi parto da qui?
No.
No, perché è un video questo.
Sì. Ma dov'è? Vabbè.
Serve l'audio. Devi fare da lui. L'audio c'è.